Right now, you are sitting on a tiny rock, circling a star so enormous that you could pour over 1 million Earths inside it and still have room to spare. And yet that star, the sun, the thing that dominates our entire sky, is nothing more than a single glowing speck in the dark immensity that surrounds it. You think you understand how big our solar system is. You have seen the diagrams in school, the neat little circles spinning around a yellow ball, all of it squeezed comfortably onto a single page. But here is the truth: those pictures never tell you. Those diagrams are a lie. Not a malicious lie, but a necessary one. Because the real solar system cannot fit on any page, on any screen, or inside any room ever built. If you tried to draw it to scale, with the planets the right size and the right distance apart, the inner worlds would vanish into invisible dots, and the outer edge would stretch far beyond the walls of whatever building you were standing in. In those familiar pictures, the planets are drawn close together, evenly spaced, all roughly the same size, marching out from the sun in tidy rows. It is a useful picture for learning the names and the order of the worlds. But it has almost nothing to do with reality. If you shrank the sun down to the size of a coin and placed it at one end of a long field, the nearest planet would be a barely visible speck, a step or two away. And the outermost worlds would lie far beyond the far end of the field, with nothing but emptiness in between. The moment you make the planets large enough to see, the distances become so enormous that they run off the edge of any picture. And the moment you shrink the distances down to fit, the planets vanish into invisible dots. This is why almost no one alive truly grasps where we live. Our home is so vast, so empty, and so silent that the human mind simply refuses to hold it all at once. We are about to fix that. We are going to travel outward, step by step, from the blazing furnace at the center all the way to the frozen, forgotten boundary, where the sun's influence finally surrenders to the dark. And by the end, the ground beneath your feet will feel very different than it does right now. Most of us go through our entire lives without ever stopping to ask what is actually above us. We glance at the moon. We squint at the sun. On a clear night, we notice a scattering of stars, and maybe, if we are lucky, a planet shining a little brighter than the rest. And then we look back down at our phones, at our streets, at the small, warm, human-sized world we live inside. That is natural. Our brains were built for the savannah, not for the void. They were shaped by millions of years of worrying about the next meal, the next threat, the next sunrise. Distances measured in millions or billions of kilometers meant nothing to our ancestors, and in truth they mean almost nothing to us now. When someone says a number like 1 billion, your mind quietly files it away in the same drawer as 1 million, or 1 trillion. They all just become really big, and the difference between them disappears. But the difference is everything. 1 million seconds from now is about 11.5 days away. 1 billion seconds from now is about 32 years away. That is the gap your brain refuses to feel. The difference between a week and a lifetime, hidden inside 2 words that sound almost the same. And the solar system is built entirely out of those numbers that your mind cannot hold. So we are going to do something about that. We are not going to throw distances at you and hope they stick. We are going to walk outward together, one world at a time, building the scale brick by brick until the emptiness becomes something you can almost reach out and touch. Before we begin, be sure to like the video and subscribe for more journeys into the cosmos. Now, take a deep breath and let's begin. To understand the scale of anything, you first need something to measure it against. So let us start with a single, honest number. Light, the fastest thing that exists, travels at almost 300,000 kilometers every second. In one single second, a beam of light could wrap around the entire Earth 7.5 times. Nothing in the universe moves faster. Hold on to that fact, because light is going to be our measuring stick for everything that follows. And the first thing it reveals is just how strange our sense of distance really is. We think we understand speed. We have ridden in cars, flown in planes, watched rockets climb into the sky. The fastest aircraft ever built can cross from one side of a country to the other in a matter of hours. But light does not measure its journeys in countries. In the time it takes you to blink, light has already traveled far enough to circle the Earth more than once. In a single heartbeat, it crosses thousands of kilometers. It is so fast that, for everything in your daily life, light is effectively instant. Flip a switch, and the room fills with light before you can register the movement of your own hand. And yet, the moment we step off the Earth, even this impossible speed begins to feel slow. That is the secret the solar system keeps. It is so large that the fastest thing in the universe, the thing that for us is instant, suddenly needs minutes, then hours, then years to cross it. Light is the one honest ruler we have, and we are about to watch even light struggle against the size of our home. When you stand outside on a clear day and feel the warmth of the sun on your skin, you are not feeling the sun as it is right now. You are feeling the sun as it was 8 minutes and 20 seconds ago. The light that warms your face left the surface of the sun while you were doing something else entirely, and it has been racing across empty space at 300,000 kilometers per second the whole time, just to reach you. That gap, 8 minutes and 20 seconds, is the distance between us and the star we orbit. It is roughly 150 million kilometers. That number is so large it becomes meaningless almost instantly. Numbers like this slide straight through our minds without leaving a mark, because nothing in our daily lives ever prepared us to feel them. It is just a string of words, a really big number, and the mind quietly gives up on it. So let us anchor it. If you climbed into a car and drove toward the sun at 100 kilometers per hour, never stopping, never sleeping, never slowing down, you would arrive in around 170 years. You would be long gone before the journey ended. Generations would live and pass while your car was still rolling toward our nearest star. And remember, the sun is the closest major object in the sky to us. Apart from the moon, it is, by the standards of everything else we are about to explore, practically next door. If it takes a lifetime of driving just to reach the sun, then hold on to that feeling, because every step beyond it will dwarf what came before. The distance to the sun is the small, familiar end of the scale. Everything else stretches outward from here into numbers that grow and grow until they leave the human imagination far behind. And that, the distance to the sun, is the very first step of our journey. It is the shortest one we will take. Now let us look at the sun itself, because everything in the solar system begins here. The sun is not just the biggest thing in our neighborhood. It is, for all practical purposes, the only thing. This single star contains 99.86% of all the mass in the entire solar system. Read that again. Everything else, every planet, every moon, every asteroid, every comet, every grain of dust, all of it added together, makes up barely more than 0.1% of what is here. If the solar system were a giant scale, the sun would sit on one side, and on the other side you would pile up all 8 planets, the dwarf planets, the moons, the asteroids, the comets, and the entire combined weight would still not come close to tipping the balance. We do not orbit the sun because we choose to. We orbit because the sun is so overwhelmingly massive that escape is simply not on the table. This single fact reshapes how you should picture the whole solar system. We tend to imagine it as the sun plus a collection of planets, as though the planets were major partners in the arrangement. But they are not. In terms of mass, the planets are almost an afterthought, a thin scattering of crumbs around one utterly dominant body. If you could somehow remove every planet, every moon, every asteroid and comet from the solar system, the sun would barely notice. It would shine on, almost unchanged, having lost less than 2 parts in 1,000 of its total weight. The sun is not the center of the solar system in some loose, symbolic sense. It is the solar system, very nearly in its entirety, and everything else is a rounding error orbiting around it, held in place by the immense gravity of that single, dominant star. The diameter of the sun is around 1,400,000 kilometers. You could line up 109 Earths across its face like beads on a string. You could empty more than 1 million Earths into its volume. And the surface you see, that blinding golden disk, burns at roughly 5,500 degrees Celsius. But that surface is the cool part. Deep in the core, where gravity crushes everything inward, the temperature climbs to around 15 million degrees Celsius. In that core, the sun is doing something almost impossible to imagine. Every single second, it converts roughly 4 million tons of its own matter directly into energy. 4 million tons, gone, every second, transformed into the light and heat that makes life on Earth possible. It has been doing this for about 4.5 billion years, and it will keep doing it for roughly another 5 billion more. The energy the sun releases in just 1 second is more than human civilization has used in its entire history, many times over. To understand where that energy comes from, you have to picture what is happening in the core. There, under crushing pressure and unimaginable heat, the nuclei of hydrogen atoms are forced together so violently that they fuse, merging into helium. Each time this happens, a tiny amount of mass is converted into pure energy, and although each individual reaction is minuscule, they happen in numbers so vast that the total output is staggering. This is the same process that powers every star in the sky, the nuclear furnace at the heart of all of them. The energy released in the core does not escape immediately. The sun is so dense that a single packet of light produced in the center can take many thousands of years to fight its way out to the surface, bouncing and scattering through the layers of the sun. By the time the light finally escapes and races across space to reach your eyes in 8 minutes, the energy within it began its journey out of the core long before human civilization existed. The sunlight warming your face today was, in a sense, created in the deep past and has only just now arrived at the surface to begin its short trip to Earth. And yet, here is the part that should unsettle you. The sun is ordinary. Astronomers call it a yellow dwarf, a perfectly average, middle-of-the-road star. In the wider galaxy, there are stars that would make our sun look like a candle flame held up against a wildfire. But for us, for everything we have ever known, this average star is the engine of all life. Think about how strange that is. Every meal you have ever eaten traces back to this star. The plants pulled its light out of the sky and turned it into sugar. The animals ate the plants. And the energy that moves your muscles, that fires the thoughts in your head right now, is, at its root, sunlight that fell to Earth and was captured and stored. Even the fuels we burn, the coal and the oil, are nothing more than ancient sunlight locked away inside living things that died millions of years ago and were buried and pressed into the ground. When you light a fire, you are releasing sunlight that fell on a forest long before the first humans existed. We are, all of us, creatures of the sun. And it does all of this from 150 million kilometers away, across a gulf of vacuum so cold and so empty that nothing should be able to cross it. Yet the light crosses it, every second, in unimaginable quantities, and only a tiny sliver of that light ever touches the Earth at all. The vast majority of the sun's energy pours out in every other direction, into the empty dark, lighting up nothing, warming no one, simply streaming outward forever. The Earth catches less than 1/1000th of what the sun gives off. And that tiny fraction is enough to power every storm, every ocean current, every growing thing, every living creature on the entire planet. So picture it now, this blazing sphere, 1 million Earths in volume, hanging in the dark. That is our starting point. Now we leave it behind and head outward toward the first of the planets. The closest planet to the sun is Mercury, a small, battered world of gray rock and iron. Mercury orbits at an average distance of around 58 million kilometers from the sun. It is a place of brutal extremes. Because it sits so close to that furnace and turns so slowly, the side facing the sun can reach around 430 degrees Celsius, hot enough to melt lead. But Mercury has almost no atmosphere to trap that heat. So the moment a part of its surface turns away into night, the warmth escapes straight into space, and the temperature collapses to nearly -180 degrees Celsius. On a single small world, you have a swing of over 600 degrees between day and night. Mercury is also strange in how it moves. For every 2 trips it makes around the sun, it spins on its own axis exactly 3 times. A single day on Mercury, from one sunrise to the next, lasts longer than its entire year. If you stood on its surface, you could, in certain places, watch the sun rise, stop, slide backward across the sky, and then resume its path, a slow, eerie dance caused by the way its spin and its orbit lock together. This strange relationship between Mercury's spin and its orbit is something we only fully understood relatively recently. For a long time, astronomers assumed Mercury always kept the same face toward the sun, the way our moon always keeps the same face toward Earth. But careful observation revealed the truth, that Mercury turns exactly 3 times for every 2 orbits, a precise and unusual rhythm locked in place by the sun's powerful gravity acting on the small, slightly lopsided planet. The result is a world where the concepts of day and year become tangled together in a way that has no parallel anywhere else among the planets, where a single day genuinely outlasts the entire year. Mercury is small, only slightly larger than our own moon, and it is already eclipsing the comfortable little diagram in your head, because the gap between it and the sun alone is 58 million kilometers of nothing, empty space. That emptiness is the real story of the solar system, and we are only just beginning to feel it. There is something else about Mercury worth pausing on. Because it is so close to the sun, it is fiendishly difficult to study. To look at Mercury from Earth, you have to stare almost directly into the glare of the sun, which is why most people have never knowingly seen it in the sky at all. It hides in the twilight, low on the horizon, just before sunrise or just after sunset, gone again within minutes. For something so close to us, it remained mysterious for a very long time. Only a small number of spacecraft have ever visited it, and reaching it is far harder than you might expect. You would think that falling toward the sun would be easy, that gravity would simply pull a probe inward. But anything launched from Earth is already moving incredibly fast, sweeping around the sun, along with our planet. To actually reach Mercury and slow down enough to settle into orbit around it, a spacecraft has to shed an enormous amount of that speed, which takes years of careful looping past other planets, stealing tiny tugs of gravity to bleed off energy. In some ways, it is harder to reach Mercury, our close inner neighbor, than it is to leave the solar system entirely. Mercury is also slowly shrinking. As its iron core cools over the ages, the entire planet contracts, and its surface wrinkles and buckles, forming long cliffs that run for hundreds of kilometers across its face. It is a world that is very slowly drying out and folding in on itself, a small, scarred survivor sitting at the edge of the furnace. There is one more strange thing about Mercury worth knowing. Despite being the closest planet to the Sun, it is not the hottest. That title belongs to Venus, the next world out, because Venus has a thick atmosphere to trap heat, and Mercury has almost none. On Mercury, the heat simply pours away into space the moment the sun goes down, and in the permanently shadowed floors of certain craters near its poles, places the sunlight has never once reached, there may be deposits of frozen ice, water ice, sitting in the dark on the closest planet to the sun, a world of fire and rock, with ice hidden in its shadows. That is the kind of contradiction the solar system is full of. Once you look closely, nothing out here is quite as simple as it first appears. Next comes Venus. And Venus is where the solar system starts to feel less like a collection of planets and more like a gallery of warnings. Venus orbits at around 108 million kilometers from the Sun. In size, it is almost a twin of Earth, nearly the same diameter, nearly the same mass. If you saw the two side by side as bare spheres, you might struggle to tell them apart. But Venus is no twin. It is a vision of how badly a world can go wrong. Its atmosphere is a thick, crushing blanket of carbon dioxide, so heavy that the pressure at the surface is around 90 times greater than what you feel on Earth right now. Standing on Venus would feel like standing nearly 1 kilometer deep in the ocean. That atmosphere traps heat with merciless efficiency. The surface of Venus sits at around 465 degrees Celsius, hotter than Mercury, even though Venus is almost twice as far from the Sun. It is the hottest planetary surface in the entire solar system. And the clouds above are not made of water. They are made of sulfuric acid. Venus even spins the wrong way, turning slowly backward compared to almost everything else in the solar system, so that on Venus the sun would rise in the west and set in the east, if you could ever see it through that suffocating haze. A single rotation of Venus takes longer than its trip around the sun. It is a world that is the right size, in roughly the right region, and yet it became a furnace wrapped in poison. A reminder that sitting near a comfortable star guarantees nothing. What makes Venus so haunting is that it may not have always been this way. There is good reason to think that, long ago, Venus might have been gentler, that it could have had oceans of liquid water on its surface, much like the early Earth. But Venus sits a little closer to the sun than we do, and over time, the heat tipped a delicate balance. Water evaporated into the atmosphere, and water vapor traps heat, which evaporated still more water, which trapped still more heat. The process fed on itself, faster and faster, until the oceans were gone entirely, boiled away into the sky. What was left was a runaway furnace that has never cooled since. This is why scientists study Venus so carefully. It is, in a sense, a warning written across an entire planet, a demonstration of how a world not so different from our own can become utterly uninhabitable when the balance of heat and atmosphere is lost. Standing on the surface of Venus, if you could somehow survive, you would be crushed, roasted, and corroded all at once, beneath a sky that glows a dull, hellish orange, where the sun is never visible through the permanent shroud of cloud. And yet, from a great distance, Venus is beautiful. It is the brightest object in our night sky after the moon, a brilliant silver point that has been called both the morning star and the evening star throughout human history. watched and named and wondered at by every civilization that ever lived. For thousands of years, before anyone knew what it truly was, people saw Venus shining low in the sky at dawn and again at dusk. And many cultures believed it was two separate objects, a morning star and an evening star. Only later did we understand that it was a single world, the same brilliant planet appearing at different times, depending on where it sat in its orbit relative to ours. It is so bright that on a clear, dark night, Venus can even cast a faint shadow, the only planet able to do so. That dazzling beauty, visible to every human who has ever looked up, hides the truth of what Venus actually is: a world of crushing pressure, searing heat, and clouds of acid. A jewel from afar, a furnace up close, and then, the third world out, we arrive home. Earth orbits at that magic distance of around 150 million kilometers. Not too close, not too far. Close enough that water stays liquid, far enough that it does not boil away. From out here in our mind's eye, Earth is a single blue pixel, a fragile speck wrapped in the thinnest possible shell of air. That atmosphere, the entire sky, every cloud, every storm, every breath any creature has ever taken, is almost nothing compared to the size of the planet. If Earth were shrunk to the size of an apple, the layer of air that keeps everything alive would be thinner than the apple's skin. Beneath that delicate film, water covers most of the surface, and on this one world, as far as we know with certainty, matter arranged itself into living things, and some of those living things eventually looked up. It is worth dwelling on that thin shell of air, because it is the most precious and fragile thing about our world. Everything that breathes depends on it. Every cloud, every storm, every gust of wind, every sound you have ever heard exists within that razor-thin layer. If you could drive a car straight up at highway speed, you would pass through most of the breathable atmosphere in under an hour. Above that, the air thins to nothing, and the cold, airless dark of space begins. The boundary between a living world and the lethal void is not some vast distance. It is a thin skin of gas, held in place only by the planet's gravity, no thicker, in proportion, than the peel on a piece of fruit. And the water is just as remarkable. Liquid water, the substance every living thing we know depends upon, exists in abundance on Earth and almost nowhere else in the solar system as open seas on the surface. When you look at a photograph of the Earth from space, that blue marble wrapped in white cloud, you are looking at the only place we have ever found where all of these things came together at once. There is something worth sitting with here. As far as we know with any certainty, in this entire vast system of worlds we are exploring, this thin blue film is the only place where life exists. Mercury is a baked and frozen rock. Venus is a crushing furnace. Mars, as we will see, is a frozen desert. The giants beyond are balls of gas and ice, with no solid ground at all. And yet here, on this one ordinary planet, orbiting this one ordinary star, the conditions fell into place so perfectly that oceans formed, and within those oceans, something began to copy itself and never stopped. Everything you have ever known, everyone you have ever met, exists on this single fragile speck. There is no second home waiting nearby. There is no backup. The more you understand the scale and the harshness of everything around us, the more precious and improbable this one blue world becomes. Our moon orbits Earth at an average distance of around 384,000 kilometers. That sounds close, and compared to everything else out here, it is. But it is far enough that you could fit every other planet in the solar system, lined up side by side, into the gap between Earth and the moon, with room left over. Stop and picture that for a moment. The moon looks close. It hangs in our sky, bright and familiar, seemingly just overhead. And yet, into the space between us and it, you could line up Mercury, Venus, Mars, Jupiter, Saturn, Uranus, and Neptune, all 8 of the other worlds, side by side, and they would still not quite fill the gap. That is how much empty space sits between the Earth and its own moon, the nearest object in all of space. If even this, our closest neighbor, is that far away, then everything beyond it is about to stretch into distances that defy belief. The moon is the farthest any human being has ever traveled. 12 people have walked on it. No one has gone any deeper into the solar system than that gray, dusty rock just 3 days away by rocket. Everything else we are about to explore, every planet, every ring, every frozen moon, no human has ever come close to. We have only sent machines. The moon itself is worth a moment of wonder, because it is far stranger than the familiar face we see each night. It is unusually large compared to the planet it orbits, so large that some astronomers describe the Earth and Moon almost as a double world. Most moons are tiny compared to their planets. Ours is more than a quarter of Earth's width. We believe it was born in violence, when a body roughly the size of Mars slammed into the young Earth, blasting a vast cloud of molten debris into orbit, which slowly gathered itself together into the moon we know. That ancient collision shaped everything that followed. The moon's gravity raises the tides in our oceans, gently pulling the water back and forth twice a day. It steadies the tilt of the Earth, keeping our seasons stable over long stretches of time, which may have been essential for life to develop as it did. And it is slowly drifting away from us, by a few centimeters each year, so that in the deep future, it will hang smaller in the sky than it does now. The moon you see tonight is closer than it will ever be again. There is a reason Earth, and only Earth, became a living world, and it comes down to a narrow band of distance around the sun. Astronomers call it the habitable zone, sometimes the zone where liquid water can exist. Too close to the sun, and any water boils away, as it did on Venus. Too far, and water freezes solid, as it has on Mars and everywhere beyond. But in a narrow ring, at just the right distance, a world can hold liquid water on its surface, neither boiling nor freezing. Earth orbits squarely within that ring. Venus sits just inside its inner edge, where it was tipped into runaway heat. Mars sits near or just beyond its outer edge, where its water froze and its air thinned away. We occupy the one comfortable band, and even within that band, countless other things had to fall into place. Earth is large enough to hold on to its atmosphere, but not so large that it became a crushing giant. It has a molten iron core that generates a magnetic field, an invisible shield that deflects much of the dangerous radiation streaming from the sun, protecting the surface and the life upon it. It has that unusually large moon, steadying its tilt and keeping its climate stable over long ages. It has plate tectonics, slowly recycling its surface, regulating its atmosphere over millions of years. Remove any one of these, and the story might have ended very differently. When you understand how many conditions had to align, the existence of a living world stops feeling ordinary and starts feeling almost miraculous. Out of all the worlds we have explored on this journey, all the rock and ice and gas, only this one fell into every narrow window at once. Only this one became a home. Now hold this image in your mind. The sun, then Mercury, then Venus, then Earth, all packed into the inner region. These first 3 planets, plus the one we are about to meet, are the rocky worlds, the small, dense, solid planets. They are the only worlds in the entire solar system with true solid ground you could stand upon. The only places with a surface in the way we understand the word. Everything beyond them, every world we are about to reach, is either a ball of gas with no surface at all, or a frozen sphere of ice in the deep cold. These four rocky worlds, huddled close to the sun, are the familiar kind of place, the kind we evolved on and can picture in our minds. And here is the thing. Everything we have described so far, all the way out to Earth, is squeezed into the cozy inner courtyard of the solar system. We have not even begun to feel the true distances yet. The fourth planet is Mars, orbiting at around 228 million kilometers from the Sun. Mars is the world that has haunted human imagination more than any other. It is roughly half the size of Earth, a cold desert of rust-colored rock and dust, its red shade coming from iron oxide, essentially rust, scattered across its surface. Mars once had rivers. We can still see the dried channels carved into its surface, ancient riverbeds, and the ghostly outlines of what may once have been lakes or seas. Long ago, Mars likely had a thicker atmosphere and liquid water flowing across the ground. But Mars is small, and small worlds cannot hold on. Over hundreds of millions of years, it lost most of its atmosphere to space. Its water froze or escaped, and the planet became the frozen, near-airless desert we see today. The atmosphere that remains is less than 1% as thick as Earth's. Mars holds the largest volcano in the entire solar system, Olympus Mons, a mountain that rises around 22 kilometers above the surrounding plains, nearly 3 times taller than the highest peak on Earth. Its base is so wide that if you stood on it, the slopes would curve away below the horizon, and you might not even realize you were standing on a mountain at all. The reason Mars can hold such an enormous mountain comes down to its nature. On Earth, the surface is broken into great plates that slowly move, so that a volcano sitting over a hot spot eventually drifts away from it, and no single mountain can grow without limit. But Mars has no such moving plates. A volcano there can sit over the same source of molten rock for hundreds of millions of years, erupting again and again in the same place, building higher and higher, until it reaches a size no mountain on Earth could ever match. Olympus Mons is the result, a single volcano grown to monstrous proportions because nothing ever moved it off its source. Mars also carries a canyon system called Valles Marineris, a vast network of chasms stretching over 4,000 kilometers long, so enormous it would reach across an entire continent on Earth. Mars has 2 tiny moons, Phobos and Deimos, little more than captured lumps of rock, irregular and potato-shaped, far too small to ever pull themselves into spheres. The larger of the two, Phobos, orbits so close to Mars and so fast that it rises and sets twice in a single Martian day, racing across the sky in the wrong direction. And like Triton far out at Neptune, Phobos is slowly spiraling inward, doomed in the distant future to be torn apart by Mars itself. Of all the worlds beyond Earth, Mars is the one we have studied most intensely. We have sent orbiters to circle it, landers to settle on its surface, and rovers to crawl across its deserts, drilling into its rocks and tasting its ancient soil. We have done all this for one reason above all others. We want to know whether Mars ever held life. If those ancient rivers really did flow, if those lakes and seas really did exist, then for a time, Mars may have been a warm, wet world, not so different from the early Earth. And if life arose here on our world, the question becomes almost unbearable. Did it also arise there, on that second world, in those vanished waters? We do not yet know. But every machine we send searches for the answer, scratching at the rust-colored dust, hunting for any trace, any whisper, that we were once not alone, even within our own solar system. Mars is also the world we most often dream of reaching ourselves. It is the one other planet whose surface a human being could, in principle, stand upon, though even that would be brutally hard. The journey alone would take many months, crossing more than 200 million kilometers of empty space, with no possibility of rescue and no turning back. On arrival, the explorers would find a world that is actively hostile to life. The thin air is almost entirely carbon dioxide, unbreathable, offering almost no protection from the radiation pouring in from space and the sun. The temperature can plunge well below -100 degrees Celsius at night. There is no liquid water on the surface to drink, only ice locked beneath the ground and at the poles. Vast dust storms can rise up and engulf the entire planet for weeks at a time, blotting out the sun. And yet, despite all of this, Mars remains the most realistic target for human exploration beyond the Moon, because everything else is worse. Venus would crush and roast any visitor in moments. The giants have no surface to stand on at all. The moons of the outer planets are unimaginably cold and impossibly far. Mars, for all its hostility, is the gentlest of the alternatives, the one rocky world within reach, where humans might one day leave their footprints in the rust-colored dust. When you look at Mars in the night sky, that steady reddish point of light, you are looking at the next great frontier of human exploration, a world we have studied from afar and with our machines, but never yet touched with our own hands. And Mars marks a kind of boundary. It is the last of the small rocky worlds, the final solid ground before the solar system changes character completely. Because just beyond Mars, the distances stop being merely large and start becoming something the human mind genuinely cannot picture. But before we cross that threshold, we have to pass through one of the strangest regions of all. Beyond Mars lies the asteroid belt, a wide ring of rocky debris circling the sun between Mars and the giant planet Jupiter. When you hear the words asteroid belt, your mind probably conjures an image from the movies, a dense, churning storm of tumbling rocks, so tightly packed that any ship would have to weave desperately to survive. Forget that image entirely. The reality is almost the exact opposite. The asteroid belt is so spread out that spacecraft have flown through it many times without any special effort to dodge anything, and the chance of striking even a small object is vanishingly low. If you were dropped into the middle of the belt, you would most likely see nothing but empty space stretching away in every direction, with perhaps the distant sun and a scattering of stars, and no asteroid visible to you at all. The crowded, dangerous asteroid field of the movies simply does not exist in our solar system. The asteroid belt is one of the emptiest places imaginable. Yes, it contains millions of asteroids, some the size of pebbles, others hundreds of kilometers across. The largest, Ceres, is round enough and big enough to be classed as a dwarf planet, around 940 kilometers wide, holding nearly a third of all the mass in the entire belt. Ceres itself is a fascinating little world. It is large enough for its own gravity to have pulled it into a sphere, and beneath its surface there may be a layer of ice and possibly even briny water. Bright spots seen on its surface turned out to be deposits of salt left behind where salty water reached the surface and the water evaporated away into space. Even here, in the middle of the asteroid belt, on the largest of these scattered rocks, we find hints of water and a more complex history than anyone expected. But Ceres is the giant of the belt. Most of its other members are far smaller, irregular lumps of rock and metal, tumbling slowly through the dark. And they are spread so thinly that the asteroid belt, despite holding millions of objects, is almost entirely empty space. But these objects are spread across such an enormous volume of space that they are, on average, hundreds of thousands of kilometers apart. If you were standing on one asteroid, you would most likely not be able to see another one at all. You could fly a spacecraft straight through the belt as we have done many times, and the odds of hitting anything are almost nothing. The total mass of every asteroid in the belt added together is less than the mass of our moon. This is your first real taste of the truth about the solar system. It is not crowded. It is mostly, overwhelmingly, almost entirely empty. The asteroid belt is not a wall of rock. It is a vast, lonely scattering of stones drifting through an ocean of nothing. These asteroids are, in a sense, leftovers. When the solar system was forming, billions of years ago, the material in this region tried to come together into a planet, just as it did everywhere else. But Jupiter was already there, enormous and close, and its gravity stirred the region so violently that the pieces could never settle into a single world. They kept colliding, shattering, and scattering, and so they remain to this day, frozen mid-assembly, a planet that was never allowed to be born. In those asteroids, locked away unchanged, is a record of the earliest days of the solar system, the raw material from which everything else was made. That is why we send spacecraft to study them, even to land on them and bring tiny samples home. They are time capsules, fragments of the beginning, preserved in the cold and the dark for 4.5 billion years. And once we cross it, the scale of that nothing explodes. Because now we leave the inner solar system behind for good, and we enter the realm of the giants. The first giant is Jupiter, and Jupiter changes everything. Before we describe it, it helps to grasp just how different the giants are in size from the worlds we have left behind. If you imagine Earth as a single grape, then Mercury and Mars are smaller grapes, Venus is roughly another grape, and our moon is a peppercorn beside them. These are the small worlds, the rocky worlds, all comparable in scale. But Jupiter, on that same scale, would not be a grape at all. It would be a large beach ball. Saturn would be a slightly smaller beach ball. Uranus and Neptune would each be about the size of a grapefruit. The jump from the rocky worlds to the giants is not gradual. It is a leap, a sudden change in category, as if the solar system contains two completely different kinds of place: the small solid worlds near the sun and the enormous gas and ice worlds far from it, with the asteroid belt marking the border between them. And these two realms are separated not just by size but by vast distance. The gap between Mars and Jupiter is greater than the entire distance from the Sun out to Mars. You cross the asteroid belt, and you have only just begun the long fall outward into the realm of the giants. Jupiter orbits at around 778 million kilometers from the Sun, more than 5 times farther out than Earth, and it is colossal. Jupiter is the largest planet in the solar system by an enormous margin. You could fit around 1,300 Earths inside it. Its mass is more than twice that of every other planet in the solar system combined. If you gathered up Saturn, Uranus, Neptune, all the rocky worlds, all the moons and asteroids and comets, and weighed them against Jupiter alone, Jupiter would still win. This is not a solid world. Jupiter is a ball of gas and liquid, mostly hydrogen and helium, the same ingredients as the Sun. In fact, if Jupiter had grown some 80 times more massive, the pressure and heat in its core might have ignited it into a star of its own, and our solar system would have had 2 suns. It came close, in cosmic terms, but never crossed that line. The most famous feature of Jupiter is the Great Red Spot, a single, enormous storm that has been raging for at least 350 years, possibly far longer. This storm is so vast that the entire Earth could fit inside it. A hurricane wider than our whole planet, spinning in the clouds of a world made of gas, churning for centuries without end. To stand in such a storm, if you somehow could, would be to be surrounded by winds screaming past at hundreds of kilometers per hour, in a sky with no ground below and no ceiling above, only ever deepening layers of cloud. The colors of Jupiter, its famous bands of cream and orange and brown, are vast belts of weather, currents of gas flowing in opposite directions at tremendous speeds, wrapping all the way around the planet. Where these currents meet, they tear at one another, spinning off smaller storms, swirls and eddies that appear and vanish over months and years. Jupiter is not a calm giant. It is a world of perpetual, planet-wide tempest, a place where storms larger than entire worlds are simply part of the weather. Jupiter spins faster than any other planet, completing a full rotation in under 10 hours, despite its immense size. That ferocious spin flattens it slightly, bulging it out at the equator. And around Jupiter swirls a court of dozens upon dozens of moons. These moons were among the first objects ever seen orbiting another world, spotted through one of the earliest telescopes more than 400 years ago. That discovery changed human history, because it proved that not everything in the sky circles the Earth. Here were 4 points of light clearly going around Jupiter, night after night, a tiny system in miniature, visible proof that the Earth was not the center of everything. It was one of the first cracks in the old idea that we stood at the middle of creation, and it helped open the door to our modern understanding of the cosmos. Those 4 large moons are worlds in their own right. Io, the most volcanically active body in the entire solar system, its surface constantly reshaped by eruptions. Europa, an icy moon hiding a vast ocean of liquid water beneath its frozen shell. An ocean that may contain more water than all of Earth's oceans combined, and one of the most promising places to search for life beyond Earth. Ganymede, the largest moon in the solar system, bigger even than the planet Mercury. And Callisto, an ancient, cratered world, scarred by billions of years of impacts. Jupiter is so massive that its gravity shapes the entire solar system. It flings comets away, captures others, and acts like a vast gravitational shield, sometimes protecting the inner worlds from incoming debris, sometimes hurling that debris inward instead. Some scientists believe that Jupiter, sitting out there like a great gravitational guardian, may have helped make life on Earth possible by sweeping up or deflecting many of the comets and asteroids that would otherwise have rained down on our world. Its immense gravity acts like a shield, catching or flinging away objects that might have struck the inner planets. Whether that role was truly protective or sometimes harmful is still debated, but there is no doubt that Jupiter's gravity has shaped the entire history of the solar system. It governs the asteroid belt, holds families of comets in line, and even keeps thousands of smaller objects trapped in step with its own orbit, leading and trailing it around the Sun. Nothing in the outer solar system is untouched by Jupiter's pull. It is the great gravitational anchor of the planets, second only to the Sun itself in its influence over everything around it. To stand near Jupiter would be to feel small in a way the inner planets never prepared you for. There is one more thing about Jupiter that is easy to overlook but impossible to forget once you know it. Jupiter does not have a surface. If you fell into Jupiter, you would never land on anything. You would simply sink, deeper and deeper, as the gas around you grew thicker and hotter, and the pressure climbed to crushing levels. The clouds would give way to a sea of liquid hydrogen, and below that, under pressures we can barely imagine, the hydrogen itself would behave like a liquid metal, conducting electricity, churning in vast currents. It is these currents, deep inside the planet, that generate Jupiter's magnetic field, the most powerful of any planet in the solar system. That magnetic field is so enormous that if you could see it glowing in the night sky from Earth, it would appear larger than the full moon, despite Jupiter being hundreds of millions of kilometers away. It traps charged particles in vast belts of radiation so intense that they would be deadly to any astronaut, and a serious threat even to the hardened machines we send. Jupiter is not just a planet. It is almost a failed star, a world of such size and power that it bends the space around it and rules the outer solar system like a king. And yet, even at Jupiter, we are nowhere near the edge. We are not even halfway. Beyond Jupiter lies the most beautiful object in the solar system, the ringed giant, Saturn. Saturn orbits at around 1,400,000,000 kilometers from the Sun. Stop on that number for a moment. 1,400,000,000 kilometers. That is nearly 10 times the distance from Earth to the Sun. Sunlight, which reached your face in 8 minutes, takes around 80 minutes to crawl all the way out to Saturn. By the time the Sun's light arrives there, it is faint and weak, and the Sun itself, that overwhelming sky-filling presence we know on Earth, would appear as little more than a brilliant, distant point. Stand on Earth, and the Sun is a great disk, large enough to light an entire world, warm enough to feel on your skin from 150 million kilometers away. Travel out to Saturn, 10 times farther, and that same sun shrinks to a fierce but tiny spark, giving roughly 1/100th of the light it gives us. A bright day on Saturn would be dimmer than a heavily overcast afternoon on Earth. The warmth is essentially gone. This is the first thing you would truly feel about the outer solar system. If you could go there, not just the distance in kilometers, but the dimness, the cold, the sense that the sun has become just another star, brighter than the rest, but no longer the ruler of the sky. And yet, even out here in the cold and the gloom, Saturn hangs in space, wrapped in the most spectacular structure in the entire solar system. Saturn is the second largest planet, another gas giant, large enough to hold around 760 Earths inside it. But despite that size, Saturn is astonishingly light for its volume. It is the least dense planet in the solar system, so light that, if you could find an ocean large enough, Saturn would float. And then there are the rings. Saturn's rings are one of the most breathtaking sights in all of nature. They stretch out over a width of hundreds of thousands of kilometers, yet they are astonishingly thin, in most places only around 10 meters thick. Imagine a structure wider than the distance from the Earth to the Moon, but as thin, proportionally, as a sheet of paper. The rings are not solid. They are made of countless billions of pieces of ice and rock, ranging from tiny grains the size of dust to chunks as large as houses, each one a tiny moon following its own orbit around the planet, all of them together catching the distant sunlight and glowing. If you could fly close to the rings, the illusion of a smooth, solid band would dissolve entirely. You would find yourself among a vast swarm of icy particles, each one orbiting Saturn at its own speed, the inner ones racing around faster, the outer ones drifting more slowly, all of them tumbling and gently colliding as they go. The rings are mostly water ice, which is why they shine so brightly, reflecting the faint sunlight back into space. And though they span a width greater than the distance from the Earth to the Moon, they are so astonishingly thin that, seen edge-on from a distance, they almost disappear entirely, a thread of light around a giant world. It is one of the great wonders of the solar system that something so enormous can also be so delicate, a structure wider than worlds and yet thinner, in proportion, than a sheet of paper. Saturn, too, has a vast family of moons. The largest, Titan, is a world unlike any other, Titan is bigger than the planet Mercury, and it is the only moon in the solar system with a thick atmosphere, a hazy orange shroud denser than Earth's own. On its surface, it is so cold that water is frozen as hard as rock. But there, methane and ethane flow as liquids instead, forming rivers, rains, and great lakes of liquid hydrocarbons. Titan has weather, seasons, and a full liquid cycle, just with utterly alien chemistry. A probe was once sent down through Titan's thick orange haze, parachuting slowly toward the surface, and it became the most distant landing humanity has ever achieved. As it descended, it revealed a landscape shockingly familiar in its shapes, with branching channels carved by flowing liquid, rounded pebbles smoothed by that flow, and broad plains that looked, at a glance, almost like a place on Earth. And yet nothing there was as it seemed. The rivers were not water but liquid methane. The pebbles were not stone but lumps of water ice, frozen as hard as rock in the deep cold. The rain that falls on Titan is a slow drizzle of hydrocarbons, drifting down through a dense atmosphere and gravity weaker than our own. It is a world that mirrors the Earth in form while being utterly alien in substance, a frozen echo of our own planet, hundreds of millions of kilometers away. Another moon, Enceladus, is a small, brilliant white ball of ice that shoots vast geysers of water vapor out of cracks at its south pole, fed by a hidden ocean beneath its surface. Like Europa at Jupiter, it is a place where some scientists quietly wonder whether life might be possible. The rings themselves hold a kind of melancholy secret. They may not be permanent. The rings appear to be relatively young in cosmic terms, and they are slowly raining down into the planet, pulled inward by Saturn's gravity, vanishing into its clouds. The breathtaking rings we see today may have formed long after the planet itself, perhaps from a moon or comet that wandered too close and was torn apart by Saturn's gravity. Its shattered remains spread into the glittering bands we now admire. And in the far future, those same rings may fade away entirely, leaving Saturn bare. We may simply be alive at the right moment to witness them, a brief, dazzling chapter in the long life of a planet. There is something humbling in that thought. The most beautiful object in the solar system might be a temporary thing, and we happen to be here to see it. Saturn is a masterpiece. Before we go further into the dark, it is worth asking how all of this came to be. How did one star and 8 planets and all these moons and rings and frozen worlds come to exist in the first place, arranged the way they are? The story begins around 4.5 billion years ago, with nothing here at all but a vast, cold cloud of gas and dust drifting in space. That cloud was the leftover wreckage of older stars that had lived and died long before, scattering their material back into the darkness. For a long time, the cloud simply hung there, slowly turning, going nowhere. And then something disturbed it. Perhaps the shockwave from a nearby exploding star rolled through and squeezed it. Whatever the cause, the cloud began to collapse under its own gravity, pulling inward, growing denser at the center. As it collapsed, it began to spin faster, the way a spinning skater speeds up when they pull in their arms. And as it spun, it flattened from a shapeless cloud into a vast, swirling disk with a dense, growing knot of matter at its heart. That central knot became hotter and hotter as more material fell into it and the pressure climbed. Finally, when the core grew hot and dense enough, nuclear fusion ignited and the sun switched on for the first time, flooding the young disk with light. Around the newborn sun, in the leftover disk of gas and dust, the planets began to form. Tiny grains collided and stuck together, growing into pebbles, then boulders, then mountains, then worlds. Close to the sun, where it was hot, only rock and metal could survive, and so the small, dense, rocky planets formed there, Mercury, Venus, Earth, and Mars. Farther out, beyond a certain line where it was cold enough for ice to form, there was far more material to build with, and so the giant planets grew enormous, gathering vast envelopes of gas around their cores, becoming the worlds we now call Jupiter, Saturn, Uranus, and Neptune. The leftovers, the pieces that never joined a planet, became the asteroids and the comets, scattered through the system and out into its frozen edges. Everything we have explored on this journey, every world, every ring, every moon, was built from that single spinning disk around that single newborn star, in a process that took millions of years and is still, in slow and subtle ways, going on today. When you look at the solar system, you are looking at the frozen aftermath of that ancient collapse, a structure that assembled itself out of a cloud of dust and has been turning quietly ever since. This structure also has a future, and it is worth knowing how the story ends. The sun has been burning for about 4.5 billion years, and it has roughly another 5 billion years of stable life ahead of it. But it will not last forever. In the far distant future, the sun will begin to run low on the hydrogen fuel in its core. When that happens, it will not simply fade, it will swell. The sun will expand into an enormous red giant, growing so vast that it may swallow Mercury, then Venus, and possibly reach as far as the orbit of Earth itself. The inner solar system as we know it will be transformed beyond recognition, the small rocky worlds scorched or consumed. The habitable zone, that narrow, comfortable band, will shift outward, and for a time, the frozen moons of the giant planets might warm. Then, having exhausted its fuel, the sun will shed its outer layers into space, casting off glowing shells of gas, and collapse down into a small, dense, fading ember called a white dwarf, slowly cooling over billions of years. The material it casts off will drift back into the galaxy, mingling with other clouds of gas and dust, perhaps one day to be gathered into new stars and new worlds, just as our sun was born from the remnants of stars that died before it. This is the great cycle of the cosmos. Stars are born, they shine, they die, and their scattered material becomes the seeds of the next generation. Our solar system is one turn of that wheel, and one day its material will turn again into something new. We happen to be alive during the long, stable, sunlit middle of the story, the brief window when a small blue world could form, cool, fill with oceans, and give rise to creatures able to look up and piece together the whole vast tale. And the most extraordinary part is that some of that dust, the very atoms forged inside stars that died before our sun was born, eventually became the rock of the earth, the water of its oceans, and the bodies of every living thing, including you. You are, quite literally, made of the same ancient material as the planets, assembled by the same forces, a part of this system as much as any world in it. Take a moment with that idea, because it is one of the most profound things we have ever learned. The atoms that make up your body did not originate on Earth. The hydrogen and the water inside you formed in the earliest moments of the universe. The carbon, the oxygen, the nitrogen, the iron, nearly every heavier element in your body was forged in the hearts of stars that lived and died before the sun was born. Those stars, at the ends of their lives, scattered their material back into space, enriching the clouds of gas and dust that drift between the stars. And from one of those enriched clouds, our solar system formed. So the iron in your blood was made in a dying star. The calcium in your bones was made in a dying star. You are, in the most literal sense, assembled from the ashes of ancient suns, gathered together on a small blue world. briefly walking around and looking up at the descendants of the very stars that made you. When you understand that, the line between you and the cosmos starts to blur. You are not separate from the solar system, observing it from the outside. You are made of it, a piece of it that has become aware. Now, with that beginning in mind, we return to our journey outward, past the last of the planets, into the regions where the sun's reign finally begins to end. But before we leave the giants behind entirely, it is worth pausing on something easy to overlook. We have spoken of the planets as the main characters of the solar system. Yet some of the most extraordinary places out here are not planets at all. They are moons. We tend to think of moons as small, dead, gray rocks, like our own. But the moons of the giant planets are nothing like that. Many of them are full worlds in their own right, each one strange and unique, some of them more interesting than the planets they circle. Consider Io, orbiting Jupiter. It is the most volcanically active world in the entire solar system. Its surface in constant upheaval, painted in yellows and oranges and reds by sulfur, dotted with volcanoes that fling plumes of material hundreds of kilometers into space. It is squeezed and flexed relentlessly by Jupiter's immense gravity, heated from within by that constant kneading, so that it never stops erupting. Consider Europa, also at Jupiter, a smooth ball of ice crisscrossed by cracks. Beneath that frozen shell lies a global ocean of liquid water, kept warm by the same gravitational flexing. That hidden ocean may hold more water than all the seas of Earth combined. And wherever there is liquid water and warmth, the possibility of life, however faint, cannot be dismissed. Europa is one of the places we most want to explore, because beneath its ice, something could be stirring in the dark. Consider Titan, at Saturn, the only moon with a thick atmosphere where rivers and lakes of liquid methane carve channels across a frozen landscape beneath an orange sky. It is the most Earth-like place we know of in terms of having a true liquid cycle. Rain falling, rivers flowing, lakes filling, just with utterly alien chemistry in a cold so deep that water is solid rock. Consider Enceladus, a small, bright moon of Saturn that sprays fountains of water vapor into space from cracks at its south pole, fed by yet another hidden ocean. When we flew a spacecraft through those plumes, we found the ingredients associated with life drifting in them, and the possibility that something could live in that buried sea remains tantalizingly open. These moons remind us that the solar system's wonders are not only its planets. Hidden in the cold, far from the sun, circling the giants, are oceans and volcanoes and atmospheres, entire worlds waiting to be understood, any one of which could rewrite what we believe about where life can take hold. Now, with that beginning in mind, we return to our journey outward, into the regions where the sun's reign finally begins to end. But to reach it, we have already crossed over 1 billion kilometers of emptiness. And the strangest part is this. We are now leaving the part of the solar system that humanity has explored in any real detail. Past Saturn, the worlds grow dim, distant, and lonely, visited only once, briefly, by a single passing spacecraft in all of human history. The 7th planet is Uranus, a pale, featureless world of blue-green haze, orbiting at around 2,900,000,000 kilometers from the Sun. That is nearly 20 times Earth's distance from the Sun. Sunlight takes around 2 hours and 40 minutes to reach Uranus. Out here, the Sun is just a particularly bright star, giving almost no warmth at all. Uranus is an ice giant, smaller than Jupiter and Saturn, but still large enough to hold around 63 Earths inside it. Beneath its calm outer layers lies a hot, dense fluid of water, methane, and ammonia, the ices that give this class of planet its name. The methane in its atmosphere absorbs red light and reflects blue, which is why Uranus glows with that cold, ghostly cyan color. But the truly bizarre thing about Uranus is the way it lies on its side. Every other planet spins more or less upright as it orbits the Sun, like spinning tops. Uranus is tipped over almost completely, rolling around its orbit on its side, its poles pointing nearly straight at the Sun. Astronomers believe that long ago, some colossal impact knocked it over. Because of this extreme tilt, the seasons on Uranus are extraordinary. Each pole spends around 42 years in continuous sunlight, followed by around 42 years in unbroken darkness. An entire human lifetime could pass at one of its poles without the sun ever setting, and then another without it ever rising. Try to imagine what that would be like. A summer that lasts longer than most human lives, with the sun circling endlessly in the sky, never dipping below the horizon. And then, a winter just as long, an unbroken night, stretching on for decades, the sun simply gone, the world frozen in darkness for a span longer than a person's entire life. The seasons on Uranus are not measured in months, but in human lifetimes. A child born at the start of one of its long polar nights could grow old and pass on before the sun ever returned to that part of the planet. It is a world running on a clock so slow and so strange that nothing in our human experience prepares us for it. Uranus, too, has rings, though faint and dark, and a family of moons named after characters from literature. Only one spacecraft has ever visited Uranus, flying past it once, decades ago, gathering what data it could in a few short hours before continuing on into the dark. We have never returned. Almost everything we know about this entire world comes from that single, fleeting encounter. Think about what that means. Uranus is a vast world, larger than 60 Earths, with rings, with at least 27 moons, with seasons that last decades and a tilt unlike any other planet. And our entire close-up knowledge of it comes from a few hours in the 1980s, when one small spacecraft swept past and then was gone forever. Everything since has been gathered from a great distance, through telescopes straining across nearly 3 billion kilometers of darkness. There are weather systems on Uranus we have watched appear and vanish through those distant lenses. Great bright clouds that bloom and fade in its frigid atmosphere. There are hints of strange chemistry, of seasons we have only ever seen a fraction of, because a single year on Uranus lasts around 84 Earth years. No human being has lived long enough to watch Uranus complete even one full trip around the sun since we discovered what it truly was. It is a world we have barely met, a pale and silent giant lying on its side in the cold, waiting patiently for us to return. And still, we are not at the edge. There is one more major world to reach, and it lies even deeper in the cold. The eighth and final major planet is Neptune, orbiting at around 4,500 million kilometers from the Sun. 4.5 billion kilometers. This is a distance so vast that sunlight, the same light that touched your face in 8 minutes, now takes around 4 hours and 10 minutes to arrive. Out at Neptune, the sun has shrunk to a tiny, intense point of light. Noon on Neptune is dimmer than deep twilight on Earth. At that distance, the sun no longer rules the sky the way it does for us. It is simply the brightest of the stars, a single intense point giving almost no warmth, and a day on Neptune would feel, to our eyes, like a perpetual deep dusk. Everything we have crossed to reach this point, the entire inner solar system, the asteroid belt, the gas giants, would lie sunward of us, all of it closer to that distant spark than we now stand. Neptune is the other ice giant, a deep, vivid blue world, slightly smaller than Uranus but more massive. And despite being the most distant major planet, the farthest from the sun's warmth, Neptune is one of the most violent places in the solar system. It has the fastest winds anywhere among the planets. Storms that scream through its atmosphere at speeds reaching around 2,000 kilometers per hour, faster than the speed of sound on Earth. How a world so far from the sun, receiving so little energy, can power winds that ferocious remains a genuine mystery. On Earth, our weather is driven almost entirely by the sun, which heats the air and the oceans and sets everything in motion. But Neptune receives only a tiny fraction of the sunlight that Earth does, 1,000 times less, in fact. By every expectation, it should be a still, frozen, quiet world. Instead, it is the windiest planet of all, with storms that outpace anything on Earth. The energy for those winds must be coming from somewhere deep inside the planet itself, from heat left over from its formation or generated in its interior, rather than from the distant sun. It is a reminder that worlds can have their own inner fires, their own sources of energy and motion, entirely independent of the star they orbit. Out there in the dark, far from any warmth, Neptune churns and roars under its own power. A vivid blue world of supersonic storms hanging at the edge of the sun's family. Neptune's largest moon, Triton, is one of the oddest moons in the solar system. It orbits backward, in the opposite direction to Neptune's spin, which strongly suggests it was not born alongside Neptune at all. Instead, Triton was likely a wanderer from the outer solar system, captured by Neptune's gravity long ago. And it is slowly spiraling inward, destined, in the far distant future, to be torn apart and perhaps form a ring around Neptune. Triton is also one of the coldest known objects in the solar system, its surface plunging to around -235 degrees Celsius. And yet even there, geysers erupt, venting nitrogen into the thin air. This is one of the great surprises of the outer solar system. You would expect a world this far from the sun, this brutally cold, to be utterly dead, frozen solid, and unchanging. Instead, Triton is active. Dark streaks across its surface mark places where geysers have flung material into the sky, carried sideways by faint winds in its wispy atmosphere. Something is still happening on Triton, deep in the cold, billions of kilometers from the sun's warmth. It is yet another reminder that distance from the sun does not mean death and stillness. Again and again, in the frozen outer reaches, we find worlds that are still moving, still venting, still changing, driven by heat from within, or by the strange chemistry of ices that behave nothing like they do on Earth. The outer solar system is not a graveyard. It is a realm of slow, cold, alien activity, full of worlds that refuse to be as dead as we expect. Neptune was the first planet discovered not by looking, but by mathematics. Astronomers noticed that the orbit of Uranus was being tugged by something unseen, calculated where that something must be, pointed their telescopes at that exact spot, and there it was. A whole world, found through the pull of its gravity before any human eye ever saw it. That discovery was one of the great triumphs of human reason. It proved that the same laws of gravity that pull an apple to the ground reach all the way out across billions of kilometers, governing the motion of unseen worlds. A few people, working with pencil and paper, predicted the existence of an entire planet, and the universe obeyed. When the telescope finally turned to the calculated spot, Neptune was sitting almost exactly where the mathematics said it would be. It was a moment that changed how humanity saw its own mind. We were no longer merely observing the heavens. We were beginning to understand the rules they followed, and to predict things we had never seen. This was a turning point in the story of our species. For most of history, the planets were mysterious wandering lights, their motions a puzzle, their nature unknown. But by the time Neptune was found, We had learned the laws that govern how worlds move, well enough to point to an empty patch of sky and say, with confidence, there is a planet there that no one has ever seen, and to be proven right. It showed that the universe is not arbitrary or unknowable. It runs on rules, rules we can discover, rules precise enough to reveal hidden worlds through nothing but careful thought and calculation. Everything we have come to know about the far reaches of the solar system, the places no human will ever visit, rests on that same foundation, the understanding that the same physics holds everywhere. And that reason can carry us where our bodies never can. Out at Neptune, the solar system feels truly remote. The sun is a distant spark. The cold is absolute. And yet the planet churns with energy, its deep blue clouds streaked by those screaming supersonic winds, great dark storms opening and closing in its atmosphere, each one large enough to swallow the Earth. It is a world of motion and mystery, hanging at the far edge of the sun's family of major planets, 4.5 billion kilometers from the fire that gives it its faint, distant light. Like Uranus, Neptune has been visited only once, by that same lone spacecraft, in a single flyby. After Neptune, that probe sailed on, out of the realm of the planets, and into the true outer dark. That lonely spacecraft deserves a moment of its own, because it is part of an extraordinary story. A small number of probes, launched decades ago, are the only human-made objects ever to journey this far. They crossed the asteroid belt, swept past the giant planets, used the gravity of those giants to fling themselves faster and farther, and then kept going, outward, never to return. These machines are now unimaginably far away, so distant that a radio signal traveling at the speed of light takes many hours to reach them, and many hours more for their faint reply to crawl back to us. They carry cameras that have long since been switched off, instruments running on the last flickers of their power, growing colder and quieter with every passing year. And yet they still whisper back to us across the void, faint signals weaker than almost anything we know how to detect, gathered by enormous dishes pointed patiently at the dark. Before one of them left the realm of the planets forever, it was turned around to take one last photograph looking back the way it had come. In that image, taken from billions of kilometers away, the Earth appeared as a single pale dot, smaller than a pixel, a tiny mote of light, suspended in a beam of scattered sunlight. Everything that has ever happened to our species happened on that one almost invisible speck. Every war, every love, every triumph, every loss, all of it contained in a dot you could hide behind a grain of dust held at arm's length. That single photograph may be the most profound thing those machines ever sent home. Not a close-up of a planet, but a portrait of our own smallness, taken from the edge of the world we are still only beginning to explore. These distances also change something we take for granted on Earth: the simple act of talking to one another. On our planet, communication feels instant. You speak, and the person beside you hears you at once. Even a call across the entire world arrives almost immediately, carried by signals moving at the speed of light. But out in the solar system, that instant connection falls apart. When we send a command to a rover on Mars, the signal, traveling at the speed of light, takes anywhere from a few minutes to around 20 minutes to arrive, depending on where the two planets are in their orbits. If something goes wrong on Mars, we cannot react in real time. By the time we even learn of the problem, it has already been happening for many minutes, and our response will take just as long to arrive back. A rover driving across the Martian surface must, in a sense, think for itself, because a human on Earth is always seeing the past and speaking into the future. And the farther out you go, the worse it becomes. A signal to the outer planets takes hours to arrive. To the distant probes beyond the edge of the sun's bubble, A single message takes most of a day to reach them, and their faint reply takes most of a day to return. A simple back-and-forth conversation with one of those spacecraft would take longer than a full day to complete. This is the strange isolation that distance imposes. The solar system is so large that even light, the fastest messenger there is, cannot keep our scattered machines in close conversation. We send our instructions into the dark and wait, sometimes for hours, sometimes for the better part of a day, to learn whether they were heard. And now, having reached the last major planet, you might think we are nearly done. You might think Neptune is the edge of the solar system. It is not. It is barely the beginning of the end. Beyond Neptune, the solar system does not stop. It opens into a vast, cold frontier that dwarfs everything we have crossed so far. The first region we encounter is the Kuiper Belt, a wide ring of icy bodies stretching far beyond Neptune's orbit. Think of it as a second, much larger and much colder asteroid belt, made not of rock but of ice and frozen gases. It is here, in the Kuiper Belt, that we find Pluto. Pluto orbits at an average distance of around 5,900,000,000 kilometers from the Sun, though its path is so stretched and tilted that at times it actually comes closer to the Sun than Neptune does. This is one of the things that sets Pluto apart from the major planets. The 8 planets follow paths that are very nearly circular, all lying in roughly the same flat plane, like grooves on a record. Pluto does not. Its orbit is noticeably stretched into an oval, and it is tilted at an angle to the plane of the planets, so that for part of its long journey it dips inside the orbit of Neptune, and for the rest it swings far out beyond it. A single trip around the Sun takes Pluto around 248 Earth years. It has not completed even one full orbit since it was first discovered. The Pluto we see today is in a part of its path it will not return to for centuries, and no human alive will ever see it come full circle. For most of the 20th century, Pluto was called the 9th planet. But as our telescopes improved, we discovered that Pluto is just one of many similar icy worlds out in this region, and so it was reclassified as a dwarf planet. Whatever we call it, Pluto is a fascinating place. It is small, smaller than our own moon, and unimaginably cold, with surface temperatures around -230 degrees Celsius. When a spacecraft finally flew past Pluto, after a journey of more than 9 years, it revealed a world far more complex than anyone expected. Mountains made of water ice, hard as rock in that deep cold. Vast plains of frozen nitrogen, smooth and young, with no craters at all, suggesting they are constantly being renewed by some slow geological process. A faint blue haze in its thin atmosphere. And a great, pale, heart-shaped region across its surface that became instantly famous around the world. That single encounter transformed Pluto, in an instant, from a fuzzy, distant dot into a real place. For most of a century, Pluto had been nothing more than a faint point of light, too far for even our best telescopes to show as anything but a blur. Then a spacecraft, after a journey of more than 9 years and nearly 5 billion kilometers, swept past it at enormous speed and, in a few short hours, sent back images of an astonishingly varied world. Mountains, plains, glaciers of frozen nitrogen flowing slowly across the surface, a faint haze in the sky. A world that, despite the brutal cold and the immense distance, turned out to be geologically alive, still being shaped, still changing. That is the recurring lesson of the outer solar system. Again and again, when we have finally reached these distant, frozen worlds and seen them up close, they have turned out to be far richer, stranger, and more active than anyone dared to expect. The dim points of light became places, each with its own character, its own history written across its surface. Out here, the sun gives so little light, that noon on Pluto is roughly as bright as twilight on Earth, just after sunset. If you stood on Pluto and looked back toward the sun, you would see no disk at all, only an intensely bright star, brighter than anything else in the sky, but a star nonetheless. The light and warmth that defines our entire world is out here, almost gone. And yet the Kuiper Belt is full of worlds like Pluto. There are other dwarf planets out here, Eris, Makemake, Haumea, each one a frozen world following its own slow, enormous orbit. Eris is especially interesting because it is almost exactly the same size as Pluto and slightly more massive. It was the discovery of Eris, a world out beyond Pluto that rivaled it in every way, that finally forced astronomers to confront the question of what a planet really is. If Pluto was a planet, then Eris had to be one too, and so did the others that were sure to follow. Rather than keep adding new planets every time a large icy world was found in the dark, astronomers drew a new line, and the dwarf planets were defined as a class of their own. Haumea is stranger still, spinning so fast that it has been stretched into an elongated, egg-like shape, completing a full rotation in just a few hours. Makemake is a bright, frozen world of methane ice, reflecting what little sunlight reaches it out in that distant cold. These are not the only ones. Astronomers believe there may be many more such worlds still waiting to be found in the outer dark, too faint and too distant to have been spotted yet. The Kuiper Belt may hold hundreds of dwarf planets, an entire population of frozen worlds, most of them still completely unknown to us. Some of these objects take hundreds of years to circle the sun even once. A single year on these worlds is longer than all of recorded human civilization in some cases. It is worth pausing on why Pluto lost its title as a planet, because the story tells us something about the solar system itself. For decades after its discovery, Pluto was assumed to be a lonely outpost, the ninth and final planet, a small world drifting by itself at the edge of everything. But as telescopes grew more powerful, astronomers began to find other objects out there, sharing the same cold region of space. Some were nearly as large as Pluto. At least one rivaled it in mass. It became clear that Pluto was not unique at all. It was simply the first and brightest member of an entire population of frozen worlds, the largest known residents of the Kuiper Belt. Astronomers faced a choice. Either the solar system had many more planets than 9, with more being discovered all the time, or Pluto belonged to a new category of its own. And so the idea of the dwarf planet was born, and Pluto became the most famous member of that new class. It was not a demotion so much as a reclassification, a recognition that the outer solar system was far richer and more crowded with small worlds than anyone had ever imagined. Pluto did not get smaller. Our understanding got larger. There is another way to feel the scale of the solar system, and it has nothing to do with distance in kilometers. It has to do with time. Because the farther a world is from the sun, the longer it takes to complete a single orbit, a single year. On Mercury, racing around close to the sun, a year lasts only about 88 Earth days. A person living on Mercury would have a birthday every 3 months. On Venus, a year is about 225 days. On Earth, of course, a year is the familiar 365 days, the rhythm our whole lives are built around. On Mars, a year stretches to nearly twice that, about 687 Earth days. But then, the numbers begin to climb steeply. Jupiter takes almost 12 Earth years to circle the sun once. A child born when Jupiter was at a certain point in its orbit would be nearly a teenager before Jupiter returned to that same spot. Saturn takes about 29 Earth years for a single orbit. Most people would live through only 2 or 3 Saturn years in their entire lives. Uranus takes around 84 Earth years, a full human lifetime, for just one trip around the sun. Someone could be born, live a long life, and pass on, and Uranus would not yet have completed a single year since their birth. And Neptune takes about 165 Earth years to orbit the Sun once. Since its discovery, Neptune has only recently completed its very first full orbit as observed by humanity. We have watched it for less than 2 of its years. Out in the Kuiper Belt and beyond, the orbits stretch into the hundreds and thousands of years, and in the Oort cloud, a single orbit can take millions of years. A comet falling in from that distant shell may be completing an orbit it began before our species existed, and will not complete another until long after we are gone. Closer, and the worlds spin around quickly, their years short and brisk. Farther out, everything slows, the orbits lengthening, until time itself seems to stretch toward the eternal. We live on a world whose year is a brief, quick beat near the center of a vast and slowly turning clock, a clock so large that its outermost hands take millions of years to move once around. But even the Kuiper Belt, vast as it is not the true edge, because beyond it lies something so large that it changes the meaning of the word solar system entirely. Up until now, every distance we have discussed, even the billions of kilometers out to Neptune and Pluto, has still been within reach of our imagination, just barely. What comes next leaves that imagination behind completely. But first, there is an invisible boundary out here that almost no one ever thinks about, and yet it defines where the sun's true domain ends. The sun does not only give off light, it also blows out a constant stream of charged particles in every direction, a thin wind of matter flooding outward through the solar system at hundreds of kilometers per second. This solar wind sweeps past all the planets, blowing comet tails away from the sun, shaping the magnetic environment of every world it touches. And it keeps going, far beyond Neptune, far beyond Pluto, carving out an enormous bubble in the surrounding space. That bubble has a name. It is called the heliosphere, and it is the true territory of the sun, the vast region where the solar wind still pushes outward against the thin gas that drifts between the stars. For an immense distance, the solar wind wins, holding back the interstellar medium, keeping the sun's domain clear. But eventually, far out in the dark, the wind weakens, and the pressure of the gas between the stars begins to push back. There, the solar wind slows, piles up, and finally stops. That boundary, where the sun's wind can push no farther and interstellar space begins, is, in a sense, the real outer wall of the solar system, the edge of the bubble we live inside. The handful of spacecraft we sent outward decades ago have actually crossed this boundary, passing out of the heliosphere and into interstellar space for the first time in human history. They felt the solar wind die away around them and the character of space change, and they reported it back to us, the first objects from Earth ever to leave the sun's bubble behind. And yet, astonishingly, even crossing that boundary does not mean leaving the solar system entirely, because the sun's gravity reaches far, far beyond the edge of its wind. The comets of the Oort cloud still orbit the sun, still feel its pull, even out there in the deep cold, far past the wall of the heliosphere. Gravity, it turns out, has a much longer reach than wind. And it is gravity, in the end, that defines the true and final boundary of our home. Surrounding the entire solar system, far beyond the Kuiper Belt, astronomers believe there exists a vast, spherical shell of icy bodies called the Oort cloud. We have never seen it directly. It is too far, too dark, too diffuse. But we know it must be there, because it is the source of the long-period comets that occasionally fall inward toward the Sun, taking thousands or even millions of years to complete a single orbit. And the scale of the Oort cloud is where the human mind finally breaks. The inner edge of the Oort cloud may begin somewhere around 2,000 times the distance from the Earth to the Sun. Its outer edge may stretch out to 100,000 times that distance, or even more. We are no longer talking in millions or billions of kilometers in any meaningful way. We have to switch to a new unit entirely. The distance light travels in a single year, a light year, which is around 9.5 trillion kilometers. The outer edge of the Oort cloud may lie close to 1 light year away from the Sun, 1 full year of light surrounding our solar system in a giant shell, like the skin of an unimaginable sphere, with the Sun as a glowing speck at its very center. To put this in perspective, the spacecraft we have launched, the fastest objects humans have ever built, the ones that have already crossed the orbits of all the planets, will take tens of thousands of years just to reach the inner edge of the Oort cloud, and tens of thousands more to pass through it. No machine we have ever made will live to see the far side. To put it another way, everything we have explored so far, all the planets, all their moons, the asteroid belt, even the distant Kuiper belt and Pluto, occupies only the tiniest central region of the solar system. If the whole solar system, out to the edge of the Oort cloud, were the size of a large city, then everything from the Sun out to Neptune would fit inside a single small building near the center. The realm of the planets, the part we usually picture when we think of the solar system, is just that small. The overwhelming majority of our home is the vast, dark, almost empty shell of the Oort cloud surrounding everything else, a region so enormous and so sparse that the comets within it may be millions of kilometers apart from one another, drifting in near total darkness, barely held by the faint, distant pull of the Sun. The Sun out there is just another star, one bright point among many, giving no warmth and almost no light. And yet those distant comets still belong to the Sun, still circle it across spans of millions of years, still feel its gravity reaching out across that incomprehensible gulf. That is the true extent of the Sun's domain, not the orbit of Neptune, not even the Kuiper belt, but this vast spherical shell, reaching out toward the very edge of interstellar space. The Oort cloud is the true gravitational boundary of the solar system, the region where the Sun's grip finally, gently, fades into nothing. It is the shore where our cosmic island ends and the open ocean of interstellar space begins. The comets that come from the Oort cloud are some of the most beautiful and humbling visitors we ever see. Every so often, far out in that distant shell, something disturbs one of these icy bodies, perhaps the faint gravity of a passing star, perhaps some slow shifting of the cloud itself. The comet begins to fall inward toward the Sun, on a journey that may take millions of years. It tumbles through the dark for an almost incomprehensible span of time, crossing the entire width of the solar system, until at last it sweeps in close to the Sun, warms, and blazes to life, growing a glowing tail that can stretch across millions of kilometers and become visible from Earth. For a few weeks or months, it hangs in our sky, watched by people who will never see it again. And then it swings back out into the dark, climbing away from the Sun, fading, returning to the deep cold from which it came, not to return for thousands or millions of years more, if ever. Some of these comets are seen only once in all of human history, and then are gone for longer than our species has existed. When you see a great comet in the sky, you are looking at a traveler from the very edge of the solar system, a piece of the original ice that formed alongside the planets, making its rare and lonely passage through the warm inner region before vanishing again into the eternal dark. These wanderers are not only beautiful, They are also a reminder that the solar system is not entirely peaceful. Comets and asteroids do sometimes fall inward and cross the path of the Earth. Most are tiny, burning up harmlessly in our atmosphere as shooting stars, brief streaks of light on a clear night. But on rare occasions, across the long ages, larger objects have struck our world. One such impact, around 66 million years ago, is widely thought to have ended the age of the dinosaurs. When an object several kilometers wide slammed into the Earth and changed the climate of the entire planet. That single collision reshaped the entire history of life on our world, clearing the way, eventually, for the small mammals that would one day give rise to us. It is a sobering thought. The same scattering of rocks and ice that fills the outer solar system, that we have admired from a safe distance, has occasionally reached in and rewritten the story of life on Earth. This is one reason we now watch the skies so carefully, mapping the asteroids whose paths come near our own, learning where they are and where they are headed. For the first time in the history of our planet, a species has the ability to see such an object coming, and perhaps, one day, to do something about it. The same understanding of the solar system's true scale that we have built on this journey is also, in a very real sense, a kind of protection, a way of knowing our neighborhood well enough to guard the one fragile world we have. And here is the fact that ties it all together, the fact that makes the entire journey snap into focus. The nearest star to our Sun, a system called Alpha Centauri, lies around 4.24 light-years away. If the Oort cloud reaches out to roughly 1 light-year, then in some sense, our solar system's outermost reaches and the outermost reaches of our neighboring star are not so impossibly far apart, in cosmic terms. But 4.24 light-years is still a distance so immense that it makes everything we have crossed seem like a single step. The fastest spacecraft we have ever built would take tens of thousands of years to travel that distance. Light itself, the fastest thing that exists, takes more than 4 years to make the trip, and Alpha Centauri is the closest star, the very nearest one. Let that settle for a moment, because it reframes everything. We have spent this entire journey marveling at the distances inside our own solar system, the billions of kilometers out to Neptune, the light-year-wide shell of the Oort cloud. And all of that, the entire vast structure, from the Sun to the very farthest comet, is just our single island. The nearest neighboring island, the closest other star, lies more than 4 light-years away across an emptiness so complete that there is essentially nothing in between. No planets, no dust to speak of. Just dark, cold, empty space, light-years of it, separating one star from the next. Consider what it would actually take to cross that gap. The fastest spacecraft humanity has ever built travel at speeds that sound enormous, tens of kilometers per second, fast enough to cross from one side of the Earth to the other in minutes. And yet, at those speeds, the journey to even the nearest star would take tens of thousands of years. If our most distant ancestors, the first humans to paint on cave walls, had somehow launched such a craft at the dawn of our species, it still would not have arrived yet. Whole civilizations would rise and fall, languages would be born and forgotten, the very face of our world would change, and still the ship would be out there, crawling across the dark, not yet halfway to the nearest star. This is the part that humbles every dream of easily roaming the galaxy. The distances between stars are so vast that they make the already staggering distances within our own solar system look small, and it tells us something profound about where we are. We are not just isolated on a single planet. We are isolated on a single island of worlds, surrounded by an ocean of emptiness so wide that crossing even to the nearest shore is, for now, almost beyond imagining. Everything we have, everything we are, everything we have ever done, is bound to this one solar system, this one grain of sand and its scattering of specks, adrift in a dark so deep that the nearest light is years away at the speed of light itself. Now let us pull back and see the whole thing at once, because only now can you truly feel it. Imagine shrinking the entire solar system down until the sun is the size of a single grain of sand. On that scale, the Earth would be a speck of dust orbiting around 5 centimeters away, far too small to see. Jupiter would be a slightly larger speck, around 25 centimeters out. Neptune, the farthest major planet, would orbit at a distance of more than 1.5 meters from that grain of sand. And the Oort cloud, the true boundary, would stretch out hundreds of meters in every direction. On that same scale, where our entire sun is a single grain of sand, the nearest star, Alpha Centauri, would be another grain of sand, sitting around 40 kilometers away. 40 kilometers of absolute, perfect emptiness between one grain of sand and the next. Let us walk that shrunken model again, slowly, because it is the only way the human mind can truly hold these distances. The sun is a grain of sand. You hold it between your fingers. Now you start to walk, looking for the planets. Mercury would be a nearly invisible mote, just a couple of centimeters from the grain. Venus and Earth and Mars, all tiny specks, all within the first few centimeters, clustered close around the sand-grained sun. This entire inner solar system, the only part of space humans have ever physically traveled within, would fit inside the palm of your hand. Everything we have ever done in space, every astronaut, every footprint on the moon, every flag and rover, all of it, contained within a few centimeters of a single grain of sand. Then you keep walking. Jupiter, the giant, would be a slightly larger speck about 1/4 meter out. Saturn, with its rings now microscopic, would sit nearly 1/2 meter away. Uranus would be roughly a meter from the grain. And Neptune, the last major planet, would orbit more than 1.5 meters out. So the entire realm of the planets, from the Sun to Neptune, would span about 3 meters across on this scale, the size of a small room. But the solar system does not end at the walls of that room. Keep walking. Pluto and the Kuiper Belt would drift somewhere just beyond Neptune, still close to that little 3-meter sphere. But the Oort cloud, the true boundary, would balloon outward to hundreds of meters in every direction, an enormous, nearly empty sphere with that single sand grain glowing faintly at its very center. And then, after all of that, after the room of planets and the vast sphere of comets, you would have to keep walking, in perfect emptiness, for 40 kilometers before you reached the next grain of sand. The next star, that is the scale. A grain of sand in a small room of nearly invisible specks, surrounded by a sphere of darkness hundreds of meters wide, and then 40 kilometers of nothing before the nearest neighbor. That is the real solar system. Not the crowded diagram from your childhood, not a tidy set of circles, but a single glowing grain of sand, surrounded by a few almost invisible specks, adrift in an ocean of darkness so wide that the next grain of sand is 40 kilometers away. This is the truth those neat little pictures could never show you. The overwhelming reality of our home is not the planets. It is the emptiness between them. We tend to think of the solar system as a place full of worlds, but it is not. It is, almost entirely, a vast and silent void, with a few rare islands of matter scattered impossibly far apart, and one bright fire holding it all together by the invisible thread of its gravity. Think about what that means for us. Every human being who has ever lived, every empire that ever rose and fell, every story ever told, every face you have ever loved, all of it has happened on that one tiny speck of dust, 5 centimeters from a grain of sand, in a void hundreds of meters across. We have never sent a person beyond the moon, a distance that, on our sand-grain scale, is far too small to even measure. The planets we have studied, the giants with their rings and storms and frozen oceans, we have reached them only with a handful of robotic explorers, machines that traveled for years across the emptiness to send back a few precious images before falling silent or sailing onward. And the edge, the real edge, out in the Oort cloud, no human and no machine has ever come close to touching it. We have only just begun to leave our own front porch. It is worth dwelling on that emptiness, because we so rarely think about it. When we imagine space, we picture it crowded, full of stars and planets pressed close together, the way they appear in paintings and films. But the reality is the opposite. Space is named well. It is, overwhelmingly, space. Emptiness. If you were placed at a random point inside our solar system, the odds are almost perfect that you would see nothing nearby at all. No planet, no moon, no asteroid within reach. Just the distant sun, a brilliant point in one direction, and the scattered stars in every other, and around you, in all directions, an immense and silent void. You could travel for years in a straight line and pass nothing. The planets, for all their size and majesty, are tiny islands separated by gulfs so wide that they almost never come near one another. Even the asteroid belt, which sounds so crowded, is mostly emptiness, its members so far apart that standing on one, you would likely see no other. This is the texture of our home. Not a busy, crowded place, but a vast cathedral of dark, with a handful of rare and precious worlds scattered through it, each one separated from the next by oceans of nothing. There is another quality to this emptiness that is hard to imagine from the surface of the earth. It is silent. On our world, we are surrounded by sound at every moment. The wind, the rain, voices, the hum of life and machinery. Sound travels through the air, and our planet is wrapped in a thick ocean of it. But space is a near-perfect vacuum. There is almost nothing out there to carry sound at all. If you could somehow stand in open space between the planets, you would hear nothing. No matter what happened around you, no matter how violent or vast, it would unfold in total silence. A storm, larger than the Earth raging on Jupiter, makes no sound that could ever reach you across the void. A comet blazing past the sun does so without a whisper. The entire grand machinery of the solar system, all its spinning worlds and screaming winds and erupting volcanoes, turns in perfect, absolute quiet. This is the true character of the place we live. Vast, dark, empty, and silent, with a few tiny islands of light and warmth and motion, and on one of them, improbably, a world filled with sound and life. And on one of those worlds, by some extraordinary turn of events, the emptiness gave rise to something that could look out and see itself. That is us. We are the part of the void that woke up. And yet, look at what we have done from this single speck. From the surface of one small rocky world, we have measured the mass of the sun, the distances to the planets, the speed of light, and the size of a cloud of comets we have never even seen. We have weighed worlds we will never visit. Consider how astonishing each of those achievements really is. We measured the distance to the sun long before any spacecraft existed, using nothing but careful observations from different points on the Earth and the geometry of how the planets move. We worked out the mass of distant planets by watching how their gravity tugs on their moons, and on passing spacecraft, reading their hidden weight from the motion of other things. We learned the temperature of Venus and the composition of Titan's lakes by capturing the faint light from those worlds and splitting it apart, reading the chemical fingerprints written in the colors. We discovered an entire planet, Neptune, before anyone ever saw it, purely from the way its gravity disturbed the orbit of another world. Each of these is a small miracle of patience and reason, performed by people who never left the ground, who never came within millions of kilometers of the things they were measuring. We have mapped a frontier no eye will ever behold. We have looked out across billions of kilometers of darkness and, using nothing but light and reason, pieced together the true shape of our home. Think about how impossible that should have been. We are creatures bound to the surface of a single planet. We cannot fly to the sun and weigh it on a scale. We cannot stretch a tape measure across the gulf to Neptune. We have never set foot beyond our own moon. And yet we know the distance to the sun, the mass of Jupiter, the temperature of Venus, the chemistry of Titan's lakes, and the existence of a cloud of comets a light year away that no human eye has ever seen. How? By watching how things move. By measuring how worlds tug on one another with gravity, and reading their masses from those tugs. By timing how long light takes to travel, and turning those times into distances. By splitting the light from distant worlds into its colors and reading, in those colors, what they are made of and how hot they are. By sending out a handful of patient machines and listening to their faint reports across the dark. Piece by piece, measurement by measurement, generation after generation, we built up the map. No single person did it. It is the work of thousands of people across hundreds of years, each adding a little more to the picture, until the true scale of our home came into focus. That, more than any single planet, is the real wonder of this story. Not just that the solar system is vast beyond imagining, but that a fragile, short-lived creature on a speck of dust managed to figure it out anyway. That is perhaps the most astonishing thing of all. Not the size of the solar system, immense as it is, but the fact that a creature standing on a speck of dust, 5 centimeters from a grain of sand, has been able to comprehend the whole. And we are not finished. Right now, even as you watch this, machines are still crawling across the deserts of Mars, still orbiting distant worlds, still listening to the faint signals of probes drifting beyond the edge of the sun's bubble. We are planning to return to the moon, to send people back to its surface, and one day, perhaps, onward to Mars, the first human footsteps on another planet. We are building telescopes that can study the atmospheres of distant worlds, searching for the faint chemical signs that something might be alive. We are designing missions to drill through the ice of Europa and Enceladus, to reach the hidden oceans below, and ask the oldest question of all, whether we are alone. Everything we have explored on this journey, every world we have described, was once just a point of light, a mystery, a guess. And one by one, we have reached out and turned those points of light into places, real places, with mountains and storms and oceans and skies. There is so much left to do. We have barely brushed the surface of our own solar system, let alone the galaxy beyond. The vast majority of these worlds we have seen only from a distance, or visited only once. The frontier is still almost entirely open. And maybe that is the most hopeful thought of all, that we live not at the end of the age of exploration, but very near its beginning, on a small world that has only just learned to look outward, taking its first uncertain steps into a solar system that is almost entirely unexplored. So the next time you step outside and feel the warmth of the sun on your face, remember, that light left its surface 8 minutes ago. It crossed 150 million kilometers of emptiness to reach you. And it is just the first, smallest step on a journey that stretches outward, past the rocky worlds, past the asteroid belt, past the giants and their rings, past the frozen dwarf worlds and the dark Kuiper belt, all the way out to a shell of ice nearly 1 light-year wide. That entire structure, that vast and silent cathedral of emptiness, is your home. Every person who has ever lived spent their whole life within it, almost all of them never leaving the surface of a single one of its worlds. Every story, every discovery, every life has played out on that one small blue speck, 5 centimeters from a grain of sand, in a void hundreds of meters across. And for nearly all of human history, we did not even know the true shape of the place we lived in. We thought the Earth was the center, the sun, a small light, the stars, tiny points fixed to a nearby dome. Only slowly, over centuries, did we come to understand the truth that we live on a modest world, circling an ordinary star, near the inner edge of an immense and mostly empty system, itself just one island among countless others in the galaxy. You live inside a grain of sand, surrounded by an ocean of dark, and yet you are able to hold the whole of it inside your mind. That is the true scale of our solar system. And the strangest, most wonderful part is that you are a part of it, looking back at it, trying to understand. You are not separate from this vast and silent system. You are made of it. The iron in your blood, the calcium in your bones, the oxygen filling your lungs right now, all of it was forged inside stars and scattered across space long before the Earth existed. It gathered together in that ancient spinning disk, became part of our world, and eventually became part of you. When you look up at the sun, or out at a planet shining in the evening sky, you are matter from the solar system, contemplating the solar system. You are a small, warm, thinking fragment of this immense cold structure, briefly arranged in a way that can wonder about the whole. For a few short years, the universe has, in you, a way of looking at itself and asking what it all means. That is the rarest and most precious thing we know of anywhere in this vast emptiness. Not the giant planets, not the rings, not the blazing sun, but the simple, improbable fact of a creature on a tiny world, gazing outward, trying to understand its home. That is the true scale of our solar system. And the strangest, most wonderful part is that you are here, a part of it, looking back at it, trying to understand. If this journey changed the way you see the sky above you, be sure to like the video and subscribe for more journeys into the cosmos.